Hello again. This is Roger Kochbar for the Bioelectricity course, Week 2, and this is our 9th segment. In this segment, we talk about membrane capacitance, and the capacitance per unit area is designated C sub m. First, it's worth asking, why does membrane have capacitance? Somehow or other, it seems very reasonable that membrane has resistance, but capacitance, well, we're not quite so sure about that. However, think about the general definition of capacitance. There is capacitance between one point and another when you have two conductors separated by an insulating region. So membranes are certainly an insulating region. So the question is, if capacitance comes from two conductors separated by an insulating region, what are the conductors? Well, let's make ourselves a sketch and talk about that. So let's suppose this is a cell in cross-section. We've said that the membrane, which is diagrammed there in red, is a very good insulator. Now this region in the interior, that's a conductor. It's not a metal plate. We think of capacitors as having metal plates because human-made capacitors are built that way, but there's nothing about the phenomenon that requires that the conductors be plates. And in fact, this solution is quite a good conductor because it's got a lot of ions floating around in it. So that's one of the plates. And then the other plate is this region outside. So this exterior volume, which is also a conductor, is the other side of the capacitor. So if we say to ourselves, capacitors have two conductors separated by an insulating region, that's exactly what we have here. A conductor inside, a conductor outside, insulating region in between. So of course it has capacitance. Let's talk about capacitors and capacitance and membrane current that flows through the capacitance as people describe it. The definition of capacitance, C equals Q over V. Take that equation and turn it around. We have Q is equal to the membrane capacitance times V. Q, of course, is the charge on the capacitor. So here's the charge right here. It's on the capacitor. I better make a note of that. Just write it in. Q is the charge. If we now mathematically differentiate the second equation, we get the third. And equation 3 says that if things change as a function of time, then dq dt here is equal to the amount of capacitance times the derivative of the voltage. And if we rearrange that equation to get equation 4, we could say dq dt is the same thing as the membrane current. It's the change in charge that's present on the membrane. So that's like a current, a change in charge per time. So Im then is the current through the membrane that's coming by because of a current through the capacitor. Now, I have made a mistake here, so I should say that's IC, the current through the capacitor. IC is equal to Cm times dVm dt. We use that equation all the time in later mathematical work, so it's very helpful. Thank you for watching this segment, and we'll go on to another one having to do with what the value of capacitance is.